So our first gas law relationship is going to be Boyle's. And by the end of our gas laws, we're going to be able to relate three variables: pressure, volume, and temperature, but we're not going to look at all three right away. Boyle, he looked at pressure and volume. And Boyle, hundreds of years ago, figured out that pressure times volume always equals a constant. It was a multiplication or product. It wasn't a divide equal a constant. So if you have a new circumstance, you can use pressure times volume before to equal the pressure times the volume at a later circumstance. So I'm adding subscript 1 now. Situation 1, pressure 1 times volume 1 equals a constant. You can go to a new circumstance, pressure 2, volume 2, and that's going to equal the same constant if, and I'll fill this if in a second. And really, you've got to control everything else. Pressure 1 times volume 1, we can figure out a second pressure and or a second volume if we keep everything else the same. So temperature must be a constant. I'm just going to put T, okay? So you can't heat it or cool it. And you have to have the same mole or moles of gas. So you can't let any gas out, you can't put any gas in. So you can't have a leak in your balloon. Boyle's law wouldn't work. So how you see it on your formula sheet is without the constant, P1 times V1 is P2 times V2, and you have to realize all the other variables are controlled. Again, you have to have a closed cylinder, closed container. Now we're going to look at the mathematical relationship between pressure and volume. As one varies, what happens to the other. Before we graph it, we're going to talk about it. We're going to look what happens when P goes up, what happens to volume. If pressure goes down, what's going to happen to volume? I've not put arrows after the V. And this relationship, pretty much everybody's played with. If you've ever played with a balloon, you realize it. You realize Boyle's law. If I have a balloon, and I don't want to squeeze a balloon too tightly because it might pop. But what happens to a balloon if I squeeze it and make the volume smaller? What does the pressure do? Yeah, the pressure is going to increase. So if you squeeze the volume goes up, pressure does, volume goes down, pressure is going to go up. It's the opposite or inverse. You know, what's hard to do, and you haven't done as a kid, is try to expand a balloon. That's not easy to do. If you did expand the balloon and make the volume bigger, the pressure would go down inside. The key I want to highlight, I'll fill in these subscripts. So in order to drive pressure up, your volume has to go down. If pressure went down, volume had to go up. Using some math language, which maybe you've seen, maybe more likely you haven't, would say pressure is inversely related to volume, or vice versa. When you say something is inversely proportional, it means they go the opposite way. If one goes up, the other goes down. One goes down, the other goes up. Inverse relationship. P is The inverse is coming from the reciprocal part. We're going to have a directly proportional relationship in a little bit. So now we're going to graph this inversely proportional relationship out. So I'm going to start with a point. So that's some pressure and volume, fairly high pressure, fairly low volume. And now we've got to use this inverse relationship. Now I'm going to put some arrows in. Don't write them in. I'm going to take them out, but I want to visually do the inverse. If I go that way on the x-axis, that would be bigger volume. So what would the pressure do? Volume gets bigger, pressure goes down. So I've got to go down with my point. Now I'm going to erase that in a second. If I do that again, bigger volume, I've got to go down again. So it's dropping. As we go higher volume, our pressure is dropping. But it's not a straight line. Drop and curve. So as the volume gets bigger and bigger, we don't see the same percentage drop or the same magnitude of drop, I should say. So this is the graphical version of Boyle's law. It shows an inverse relationship. It's not linear. So you need to know Boyle is, well, your formula sheet has it. You need to know it's Boyle. You need to know it's an inverse relationship, and you should be able to do the graph or identify a graph. We're going to look at volume and temperature next. Charles's law. Now, the multiplication type relationship didn't work when he played with volume and temperature and tried to get a constant for a given system where everything else was controlled. But when he did the ratio or divided the two, he was able to get a constant. Now that constant means you have to be at same pressure. Got to control that, and you have to keep the same number of moles. You can't let any gas out. You can't put any new gas in. No leaks. So if you keep things controlled, then you can compare two different circumstances. And Charles's law is volume divided by temperature. It's a ratio, not a product relationship. Multiply by divide. Volume 1 divided by temperature 1, we can use to predict volume 2 or temperature 2. After we've either heated the system or changed its volume. I'm going to highlight a comment from the previous lesson. We're talking about temperatures now. So you have to use Kelvin for any measurement. You can't use degrees Celsius in this relationship. Let's have that same type of discussion. What's going to happen now? We want to think our way through it. So we have a gas, but it's got to be in some sort put a certain thing so the pressure is going to stay the same. If you have a gas and you heat it up, so my balloon in my hand is a visual. You heat this up, make it hotter and hotter. The volume is going to expand. Things are going to move faster. They're going to hit the wall harder. And if the pressure is going to stay the same, the container's got to get bigger to handle those faster molecules. If you cool it down, you take a balloon, you put it in your freezer, it will shrink as you cool it. Let's put some arrows to this. So as you heat the balloon, the volume goes the same way. If the temperature goes up, the volume goes up. That wasn't like Boyle's law. If you cool your system, you're going to cause it to have a lower volume. So this is not inversely proportional. They go up together, they go down together. This is directly proportional. Temperature is proportional to volume. So that middle symbol is a proportional symbol. Kind of looks like a fish, maybe. If I wanted to say inverse, I'd put a 1 over. Then you need to be able to identify this graphically. Now I'm going to do the same thing as before. I'm going to put a point in, and then don't write the arrows. We're going to put some I'm going to put some arrows in to figure out what's going on. Now I'm going to drop in temperature, and I would need to drop in volume. And I would need to drop, if I drop the temperature again, I would drop in volume. So we're going to see a dropping as I head towards the origin. I take out my arrows, and we find out we get a linear relationship this time. We end up with a straight line. And if we look at where it crosses the temperature scale, it is going to cross it at absolute zero. In my previous lesson, I put some graphs up just like this to kind of explain where we predicted absolute zero from. So the number will change. If I do a Kelvin scale, it's going to go through 0. If I do a degree Celsius scale, it's going to go through minus 273 or 273.15. So directly proportional, straight line, negative slope to our graph. So that's Charles. And that's really all we need to put everything together. We know pressure and volume are inversely proportional. They're a product of each other. Temperature is a divide by for Charles' relationship. And when you put everything together, you get the combined gas law. Sort of literally combining Boyle and Charles. We have the pressure times volume of Boyle and the V over T of Charles. There's Boyle. You don't have to circle this in your notes. It might be cleaner if you don't. And now the only thing that has to be constant is that gas. Has to be the same gas, and we can't let any in. We can't have any. So this would work fairly well on a balloon-ish type circumstance. We can now change the pressure, the temperature, and/or the volume of this balloon, and predict is it going to get bigger, smaller, hotter, colder. What's going to happen to the pressure. So P1 times V1 over T1 is P2 times V2 over T2. Now, depending on your algebra skills, you may or may not like dealing with those denominators and moving them around. You can always cross multiply and have no denominators. But I want to highlight the subscripts. It would be P1, V1, but when we cross multiply, it gets crossed with T2. If I do the other cross, P2, V2, but it's T1. And now you can solve for any variable or isolate any one. Maybe a question asks you about T2. Well, we need T2 all by itself, so we'd have to move everything to the other side. We'd have to divide by P1 to get rid of it, divide by V1. I'm going to do one example using the combined gas law, and then you need to practice using it. So we're going to have a lot of numbers, a lot of data, because we've got 5 potential pieces. One of them will be missing. So I fill a balloon in Nova Scotia with 20 liters of air. So 80% oxygen, 80% nitrogen, 20 oxygen. I do it at 25 degrees Celsius. I take this balloon to Alberta, where the pressure has dropped from pretty much atmospheric, 1 atmosphere or 101.3 kilopascals in Nova Scotia, to 89.3 in Calgary. These are all pretty reasonable numbers. I'm wondering, what is the volume of my balloon in Calgary? And I did this in winter. It's minus 30. I'm freezing in Calgary. I grew up in Nova Scotia, where it never gets to minus 30. I never experienced minus 30 until I went to university in Ontario. And I went visiting a friend in Sudbury. It was minus 35, and I walked outside with no hat and mitts to go to another building. I didn't make it. You can't walk around with no hat and mitts at minus 35. So in this gas unit, you're going to end up with a few relationships. Your first goal is grabbing your strategy. The P1, V1 over T1, the combined gas laws, when there's no mass gas amount changing, when there's a before and after with P, V, and T. So that's what's going on here. So P1, V1 over T1 equals, now I want to color code. It's super easy to mix up your 1s and your 2s. So I'm going to make black my 1s, my 2s will be red. P2, V2 over T2. Now the 1s and the 2s don't matter where you assign them, but you have to be consistent. So I'm going to make Nova Scotia my 1s, and Alberta, my second circumstance, is going to be all my 2s and my reds. So I'm going to go read the question, color code things. So I fill a balloon in Nova Scotia with 20 liters. The Nova Scotia is 1, so that's my V1 at 25 degrees Celsius. So that's still Nova Scotia, so that's my T1. I take it to Alberta. The pressure's dropped from 101 in Nova Scotia, so that's still a 1. So that's P1. To 89-ish in Calgary. So that's our first Calgary bit of data. So that's a P2. What is the volume of the balloon in Calgary? So volume in Calgary, that's V2. And that's what we're asked about. We don't know that. The temperature is now minus 30, so that's our T2. Super easy to cross data and put it in the wrong side relationship. So I need to solve for V2. Now I'm going to fly through the algebra. There's always a few ways to do the algebra. You could cross multiply, get rid of any denominators, or you could just start moving variables around. I'm going to do it orally. I'm not going to show all my steps. I want to get V2 by itself. So the T2, which is on the bottom, I have to bring to the other side away from my V2. And the P2, which is right next to my green circle, I need to move that to the other side so it'll show up on the bottom. So the T2 is going to go to the top. The P2 is going to go to the bottom. So V2 is going to equal P1, V1 over T1. The T2 is going to go to the top. And the P2 to the bottom. So that sets how I need to solve this. Try to plug that all into a ratio on the right-hand side of the board. Now, you can use any units you want as long as A, they're absolute, so no Celsius, and B, they match. So any pressure units can work, any volume units, again, just have to be matching. So let's get started. I'm going to start with my pressures. P1 is 101.3 kilopascals. Once I've decided to use kilopascals for P1, P2, which is on the bottom, has to be in the same units. And good, it's in kilopascals, so I don't have to use any of my gas law pressure conversions to convert it. Okay. If it was in atmospheres, I would have to convert. 89.3. So I've taken care of my P1 and my P2. I'll do T2 and T1 next. So T2, the final temperature, that's the Calgary one, that's minus 30, but I can't put minus 30 in, I need it in Kelvin. So I have to convert that to Kelvin, so I have to add 273 to it. The other, or 273.15. When I do that, I get 243 Kelvin. You would keep all your digits in your calculator, don't round. I know I didn't write all the decimal places out, but you're leaving all your decimal places. T1, that's T2. T1 is the 25, and I have to add 273.15 to that, so that's 298 Kelvin. Again, I didn't write out all the decimal places to make things fit on my board, but you're keeping all your digits. Last, we've got V1, the original volume, which is 20 liters. So I barely fit everything in. Double check our units. Kilopascals kills kilopascals. Kelvin absolute kills Kelvin absolute. The volume liters the volume units I put in was liters. So my answer is going to be in liters. If I put this in milliliters, then my answer would be in milliliters. It doesn't matter what this unit is. It's going to be our output unit. grab your calculator, crunch everything, leave all the decimal places in. And sig fig wise, 3 is the lowest amount of sig figs we have. So I rounded this to 18.5 liters. So we can't do a direct or inverse relationship because we've got all the variables moving. So it's hard to predict. You might guess that the temperature has dropped so much that you might be expecting a lower volume. That's kind of what plays out here, but you can't make predictions like you can with Charles and Boyle all by itself. So in practicing, I wouldn't do a lot of Boyle and Charles, maybe do a problem or two, and I'd spend most of your time using the combined gas law. You're making sure you're good at the algebra, you're watching your unit conversions, and you're getting used to not putting degrees Celsius into your calculations. And this is something I hope you have a high degree of success with.